Hi everyone, my name is Olumayokun Ogunbekun,
And I'm Norikazu Honda.
and we are both students at Illinois Institute of Technology, Chicago, and we both major in mechanical engineering.
Right now we're doing a failure project in the summer course called the Design of Machine Elements.
The aim of the project is to go online and look for devices or materials that have poor customer reviews. We're supposed to look for where the failures are occurring in these devices and look for how best to make improvements on these devices to make them more efficient.
So we selected a T-handle spark plug socket, which looks like this. So a spark plug is a device for firing an explosive mixture into a combustion chamber in an engine. So you can find those things inside of a car, a plane, or any kind of automobile. So what this does is to remove the spark plug inside of an engine.
So the reason we chose this device is because it's an easy, everyday household device that you find in people's garages, the trunks, or their households. And based off of the reviews online, a lot of people complained that the device wasn't removing plugs as efficiently as it was supposed to be. A lot of people complained that in his first try, the handle broke and it wasn't gonna work. And a lot of people also complained that the socket wasn't fitting into the plugs properly. A lot of people complained that there wasn't enough friction to remove the plugs or to tighten or loosen the plugs.
So this is entirely made out of steel, and the top is covered with plastic. And inside of the socket, there's a grommet made out of rubber.
This device works in two ways. The first way is the vertical way, where you just apply the socket into the plug and twist it to remove, tighten, or loosen the plug. The other way is to twist it in this motion. We do this because of how flexible it is for the whole device to get into the engine, because the plugs may be further inside the engine and it may be hard for us to reach the plugs in this manner.
So when you twist it in this way, there's a torsional energy inside of the bar, and the energy goes all the way to the bottom. If you twist it in this way, there's a different types of energy in the bar, which in this case you bend it instead of twisting it. And the contact of the metal, which will make the stress concentration different inside of different areas of the metal. So based off of the reviews and based off of our educated assumptions and guesses, that we predict that the highest concentration or the highest failures may occur at the top of the T. We also predict that at the bottom of the T, where it's thinner and has less cross-sectional area, it may fail. Also, the pins that attach everything together may also break due to the stresses in torsional, bending, and even axial. And inside of the socket, there's a grommet, which may also come off due to the over twisting and then the friction. As you can see, we did a couple calculations and illustrated the model in the front view, the side view, and here are the components. The circle region shows our suspicion of high failure, high stress concentration. For our calculation, we wanted to select one particular spot where it seemed the most crucial, and that is this spot. Instead of calculating the stresses in each of these other parts, we used the Autodesk Inventor and the stress analysis to find out how much stress it is occurring in these other certain points relative to the point that we actually calculate. Earlier in this video, we demonstrated the two different methods of using this material. One of the techniques shows a bending energy throughout the bar. We found out the bending stress occurring at this spot to be 616 times the force we apply on the handle, pound force per inch squared. We know that the yield stress of this material, the stainless steel material, is 72,808.9 pound force per inch squared. The ultimate stress is 124,732 pound force per inch squared. If we use all of these information, we know that if we apply 18.196 pound force, it will yield, and if we apply this much, it will break. We know that human strength is capable of applying these amount of force. If not, you can even apply a force multiple times for it to weaken, for the material to weaken. So that is a part that we have to be careful. Another method is applying a moment like this, where it causes this arm to rotate in this way, so there will be twisting. The shear stress that we calculated through the method of cutting bars shows that if we apply a 0.54, shows that there is a stress, the shear stress at that spot of 0.54 times the force we apply on the handle of pound force per inch squared. Again, here are the yield and ultimate shear stresses, and these show the forces that will make that particular spot to yield and break. Now, we won't have enough torque or leverage, so we should be more concerned about technique 1. As you can see, after a couple tries, the bar is already bent quite a lot. We're going to give a couple tries until it breaks.
What the? Oh. What the? Yeah.
Look at that. It bent
That's
that
how
much.
bad it has bent now. Oh!
Sort of fatigue, Dad, so.
There it goes.
Fatigue has to do with it,
Yep.
but it broke.
Gotta focus. Just